Hi, let's discuss the simulation of an object falling under gravity with an air resistance. My name is Lantop. In this video session, we are going to discuss the simulation of an object falling under gravity with air resistance. So we'll perform the simulation in Matlab software. Then we're also going to go through the mathematical model that is being formulated below. I would love you to subscribe to my YouTube channel to get simulation and other mathematical formulation like this, then all sorts of machine learning code in Python and in Matlab as well. So let's get started with this session. So given an object falling under gravity, so let's say a ball or any kind of object falling under a gravity from a particular distance, and we have an air resistance that we have taken into consideration. The object is falling under a gravitational force, which we define as Fg equal to mg, which is the mass of the object times the acceleration due to gravity. Then we have an air resistance, which we define as Fr, which is C times V. This C is coefficient of drag, and the V is the velocity. Given the gravitational force and the air resistance force, we have the net force that we defined here. The net force is the difference between the gravitational force and the air resistance. It is ideal that the gravitational force is far, far greater than the air resistance. So based on this expression, we have this, which is mass times acceleration due to gravity minus the coefficient of drag multiplied by velocity. We know that this difference of this will give us the net force, which is F net. So we have the mass times acceleration. The resultant force of this is this. So let's proceed with the mathematical formulation. We can divide all terms by the mass, which is m. So if we divide all terms by the mass, we have this acceleration equal to g minus c times v divided by m. Replacing this a by the v dt, which is derivative of velocity with time. So we have this expression. So given this particular expression, we can replace c over m by k, since c is a constant. The coefficient of drag is a constant, which is constant for a particular location and particular situation. Then we have the mass, which is also a constant. So replacing c and m with a constant k. So our formula is being resulting to this. So we have dvdt equal to g minus k times v. So these are resulting formula. So this form an ordinary differential equation. With this, we're able to form the first ODE, which we call the ordinary differential equation. So given that we have the first ODE, we can get another ODE, another ODE, second ODE. The second ODE is simply the derivative of the distance. The distance traveled by the object falling is given by the velocity. So we all know that the change in the displacement is velocity. So, but in this case, we have a negative velocity, or we say a negative distance, because if an object is falling at a particular distance h, let's say 100 meters, then we know that the distance will keep on reducing, definitely velocity is equal to this because the change in displacement is negative. So we have displacement divided by dt. Given this equation, we can also rewrite it as this. So we have two systems of ordinary differential equation. So these are the two systems of the equation. Equation 1 given by change in displacement dy dt minus v and dv dt g minus k times v. So that's what we have. This is the mathematical formulation of an object falling under gravity with air resistance. So now, if we are given this problem, mass, if we have a mass of an object which is 70 kg and coefficient of drag is 0.3 kilogram per seconds, then we have the acceleration due to gravity 9.81 meter per seconds. Then we have an initial velocity which is 0. Then we have height of 100 meter. The object is falling from an height of 100 meter. Now let's now move to Matlab to see how we can use the ODE 45 solver to perform this simulation. This is Matlab. I'm going to write an ODE code here. We start by defining the ODE function. In the ODE function, I have to specify my equations. Given that I have t and x as the inputs of this solver, t is time and x is a combination of my variables. I have two variables, which is the displacement variable x of 1 and the velocity variable, which is x of 2. Then I can write my equation 1 to be equal to minus b. And I can write my equation 2. Let's look at equation 2 again. G minus k times v. G minus k multiplied by v. So we know that our G is 9.81 acceleration due to gravity. And then our P is equal to C over M. Let's confirm that again. Yeah, our K is equal to C over M. C is 0.3. Then M is 70 kg. So with this, we define equation 2. We can combine these two equations to our equations variables. To be equal to equation EQT1. I'll make sure that it is a column vector EQT2. Yes. So I've been able to define the ordinary differential equations. Now I'm going to use the ODE solver, ODE 45 solver. So I'm going to say ODE 45 So the 45, I have to define the ODE function. I have to call the ODE function. Then I have to define my T-span. Then I have to define my initial position. So my variables. So we can say initial position of variables is equal to initial point of the y0 and v0. So we know that our y0, the object is falling from 100 meters based on what we defined. Then our initial velocity is 0. Then we can also say our T-span, we want this simulation to run for just 5 seconds, 0 to 5. So this is our ODE function. Then I can write the expression to collect the output like this. So with this, we are finished writing our code. We will try to run and fix any issue in case we have. Okay, so this one successfully, we have our X and Y, X and Z. So I'm going to try to extract the positioning from here. The positioning is Y, the first point from Y. So you can see we have 69 points. The positioning is the first point from the Z. Oh, sorry. So the positioning is the first point from the Z. Then our velocity is this second column from the Z. So first column position and second column. So I'm going to plot it for us to see how the graph looks like. So that's position. So let me plot it into figure. Figure 1 is for position plots. Figure 2 is for velocity plots. Okay, so let me just put some labels. X label time, Y label. So I'm going to call this displacement. So I'm going to call this X label time, Y label velocity. So let's run this again. So this is the plot we have. We have the plot. Okay, please. Okay, this is the plot. The plot is coming up now. Let me close up plot first. Close up. Then I'll wait to run. I'll try to run again. This is the first plot. Yeah, these are the plots. So you can see the position plots. So the position plot shows that the object is falling from an height of 100 at time 0. So an height of 100, then it's going to get to this around 4 point something. It's going to get to the ground floor. So which is the distance of 0. So we see an height of 100 from the distance of 0 from the ground floor, then the object is going to get to the ground floor around around 4 point something. Something like that. So how about this? This is the velocity plot. The velocity of the object will keep increasing until you get to the ground floor. So this is the simulation of an object falling under a gravitational force with an air resistance. So you can edit this particular code. I'm going to leave the source code link in the video description, so you can find the code, edit it to solve problem for your own case study. Then for this simulation, you can always come back to it to review it, and this could be adjusted in case you have some external force pushing it. Thank you so much. Thank you so much for your time. So I'll beg you to subscribe to my YouTube channel again to get more videos relating to simulation in Matlab. Yeah, bye.